All right, welcome to page 2 of 4.6, or actually just page 2 of 4.7, Cauchy-Euler equations. And so what if we have repeated real roots? So what if our m sub 1 is equal to our m sub 2? Well, if that's the case, it's going to be very similar to previous examples where we've had the same solutions for m sub 1 and m sub 2. So if we're dealing with this equation, ax squared times d times the second derivative plus bx times the first derivative. So if we're dealing with this second order differential equation, and I'm going to go ahead and try using the auxiliary equation for a Cauchy-Euler equation, I realize that I get an m sub 1 and m sub 2. What I would want to do is I want to rewrite this in terms of a second order linear equation. And so I'd get the second derivative by itself plus bx divided by ax squared. I'm just going to show this, plus c divided by ax squared times y equals 0. I get my leading coefficient to be 1, so now it's a second order linear differential equation. And I can find my second m sub 1 using an integrating factor. In this case, the p of x is going to be whatever values with the middle term, which would be b over ax, because the x's would cancel out. And then I'd use integrating factor, and I would solve for my y. And what I would realize is that when I solve for the y, this is what I'm going to get, just to skip and save some time. This is what the solution should look like for repeated real roots, where it's going to be c sub 1 times x to the m sub 1, so that's going to be the same, plus c sub 2 times x to the m sub 1, so that stays the same, but then we're going to multiply that by the natural log of x. So the only thing that's introduced when you have repeated real roots is this natural log of x. And you can see this when, after we find our integrating factor, we take both sides, we solve for y, and this is our solution. This is what we would get. And just to save some time on the video, I'm not going to show that, but again, if you would like to see that, just email me and I'll write that out for you. So now we're going to solve this given differential equation, and more than likely we're going to have repeated real roots. So I look at this, I see it's a Cauchy-Euler because I have 4x squared y double prime. And so I'm going to look for my a's, my b's, and my c's. And so my a is 4, my b is 0 because there is no x, and my c is 1 because that's what the y. And so now I'm going to plug it into the form am, so it's 4m times m minus 1 plus bm, which is 0, plus c, which is 1, and set that equal to 0. So that's going to be 0. So that's going to go away. The bm is going to go away. Distribute the form. We get 4m squared minus 4m plus 1 equals 0. Now, again, I want to factor this. You can factor, there's multiple ways I could make this 2m squared. Actually, I just break that up to be a 2m in the middle. So it'd be 4m squared minus 2m plus 1. That way I have 4 terms. Or, I don't know if you were taught this, but multiply the last times the first. Called the Martinsville method. But after you do that, after you factor, what we're going to get is we're going to see that we're going to have 2m minus 1 squared equals 0. And so that means that our m sub 1 and our m sub 2 are going to be the same, and it's going to be equal to 1/2. And so then I plug this into what my solution should be, and let me box that up because this is what our solutions are going to be when we have repeated real roots. And I'm going to get y is equal to c sub 1 x to the 1/2 plus c sub 2 x to the 1/2 times natural log of x. And I'm finished. Now, what if you have repeated roots and you have, say, 3? Say you do a differential equation to the third order, and all the roots are going to be, 1/2. Well, then all you'd have to do is you just write this again and be plus c sub 3 x to the 1/2 times the natural log of x squared. And you can see that down here, which really didn't print off. And so you just keep repeating it up until, how many times it repeats minus 1, and that's the power that you're going to have with natural log of